In this video, we're going to be finding the limit of a rational function with non-polynomial terms. So if my memory doesn't fail me, so far the rational functions we've taken a look at, and by rational function I mean a function with like a numerator and a denominator. For example, like the limit as x tends to infinity of x to the fourth plus 3x squared plus x plus 1 divided by, I don't know, 2x to the fourth plus 5x. Let's say this is a rational function of the type we took a look at. All the terms are polynomial terms. That means they're like x raised to some integer power. But in this the example we're going to look at here has terms that are non-polynomial terms. So the limit we're going to be looking at in this video is the limit we're going to be finding in this video. Limit as x tends to infinity. Numerator you have 8x to the 6th plus 5x, or minus 15x to the 5th. I'll just erase this and rewrite it. Okay, so the limit as x tends to infinity of 8x to the 6th minus 15x to the 5th plus 10 times the square root of x divided by 3x to the 6th plus 2000x to the 5th minus ln of x. Now some of you may be able to look at this and find the answer just by realizing that as x gets bigger and bigger relative to this x to the 6th term in the numerator, this x to the 5th term and this square root of x term, these become increasingly irrelevant, and the numerator can be approximated by 8x to the 6th. And the denominator, the x to the 5th term and ln of x term become increasingly irrelevant. And as x gets really big, the denominator can be approximated by 3x to the 6th. And you divide 8x to the 6th by 3x to the 6th, the x to the 6th cancel, and you get 8/3. But I should say equal because in the limit it is equal. But if you didn't see that, then what we can do is do what we did with some of the other rational functions. And that's dividing both the numerator and denominator by the highest power of x. So I'm just going to rewrite this here so you can see it. It's 10 root x divided by 3x to the 6th plus 2000 x to the 5th minus ln of x. So we are going to be dividing both numerator and denominator by x to the 6th. So 8x to the 6th minus 15x to the 5th plus 10 root x. So we divide this whole thing by x to the 6th. Denominator 3x to the 6th plus 2000 x to the 5th minus ln of x. Divide that by x to the 6th as well. And so we have the limit as x tends to infinity, and realize that this applies to both the numerator and denominator. So this is for this fraction here, so I just rewrote it. That was kind of misleading, made it seem like it only applies to this, but this limit is of this entire complex fraction here. So we divide the numerator by x to the 6th. The first term, 8x to the 6th, divided by x to the 6th becomes 8. Minus 15x to the 5th divided by x to the 6th becomes minus 15 over x. 10 times the square root of x divided by x to the 6th is just right, plus 10 square root of x over x to the 6th. The denominator, 3x to the 6th over x to the 6th is 3. 2000 x to the 5th over x to the 6th is 2000 divided by x. And minus ln of x divided by x to the 6th, we'll just write that as it is. And now we have to look at each of these terms and see what happens as x gets bigger and bigger. So working with the numerator, 8's going to just be 8. It's not dependent on x. As x gets bigger and bigger, 15 over x is going to become closer and closer to 0. So we have 8 minus 0. Here, 10 times the square root of x is going to get bigger and bigger. Like the square root of x is going to get bigger and bigger as x gets bigger, but not quite as fast. So like when x is 100, square root of x is only going to be 10. When x is 900, the square root of x is only going to be 30. So it's going to grow as x grows, but not as fast. This denominator, however, is going to grow much faster than x grows. So when x is 10, x to the 6th is going to be 10 to the 6th. When x is 100, it's going to be 100 to the power of 6. So this denominator, as x grows, this denominator is going to really overpower the numerator. So you'll have something much smaller divided by something much larger. And as x gets increasingly larger, this numerator will become tiny in comparison to this denominator. So as x tends to infinity, this fraction will tend to 0 because this numerator will become incredibly large, or this denominator will become incredibly large relative to the numerator. Now working in the denominator of this complex fraction, limit as x tends to infinity of 3 is just 3. It's not dependent on x. And as x gets really big, 2000 over x is going to get closer and closer to 0. 2000 is a big number, but you divide 2000 by 10 million, that fraction is small. You divide it by 10 billion, now you're getting even closer to 0. Now what do you make of ln of x? Well, you have to think, what is the ln function? Well, ln of x basically says, so here's ln of x, it says to what power, so this is what ln of x is asking. To what power do I raise e? The number e is approximately 2.718 to get x. So ln of 10 will be something a bit smaller than 3, has to be raised to what power to get x? Well, 3 squared is 9, something a bit bigger than 3. Or to raise 3 to get 10, the power that you have to raise 3 to get 10 will be something a little bigger than 2, because 3 squared is only 9. If you want to raise something smaller than 3 to get 10, you're going to have to raise it to something a bit bigger than what you had to raise 3 to get 10. So but what you can see though is let's say we wanted to find the ln of 100. That would be, to what power do I have to raise 2.718 to get 100? And let's say 2.718 is right around 3. 3 to the 4th power is 81, but 3 to the 5th power is 243. So say somewhere like 3 to the 4.1 or 4.2 might give you 100. So if you want to raise 2.718 to some power, you guess maybe it'll be like 4.5 or so. So ln of 100 may be around 4.4 to 4.5. But what you can see is, for any given value of x, any given value of x bigger than 1, you can see that ln of x is going to spit out a number bigger than 1, but that number is going to be smaller than x. For example, you put in 10 for x, ln of x is only going to be 3 point something. Put in 100 for x, ln of x is only going to be, or sorry, when you put in 10 for x, ln of x is only going to be 2 point something. You put in 100 for x, ln of x is only going to be 4 point something. So it's going to be, when you take the ln of a number, it's going to be making that number smaller. So when x gets really big, ln of x also gets bigger, but not as fast as x gets big. And you'll be dividing by a quantity that's going to be making x increasingly large. Well, and that's going to be increasing much faster than x increases. So you take a number and you raise it to the 6th power, it makes that number much bigger. Well, ln of x, you take that number and you take the ln of it, it makes it smaller. So as x gets bigger, this x to the 6th in the denominator is going to get huge relative to this ln of x. So you'll have something bigger divided by something that's huge relative to what's in the numerator. So as x gets really big, ln of x over x to the 6th will approach 0. So in the numerator we have 8, in the denominator we have 3. So this limit is 8/3. Again, some of you may have been able to just tell by looking at the numerator and denominator of the original expression here, and just be able to tell that these x to the 6th terms dominate as x gets bigger. These other terms become increasingly irrelevant, so you get 8/3. But for those of you who weren't able to see that, we just divide both numerator and denominator by the highest power of x, which is x to the 6th. And then we'll see that some of these other terms, or all the other terms besides the x to the 6th terms, what was originally the x to the 6th terms, drop to 0, and we're left with 8/3.